Hello everybody, my name is Satwika Nino Wandhana, you can call me Nino, and I am with my partner Rakai Andaru Priandra, you can call him Rakai. And today we are going to present an interesting topic related to the computer science field, which is P versus NP. Here we're going to explain the explanation of P, NP hard, and also the NP complete.
What is P versus NP problems? Understanding the famous P versus NP problem is all about understanding the definitions. Let's check the definitions of P, NP, NP complete, and NP hard. And then understand the implications of P equals to NP and P is not equals to NP. First of all, P, or polynomial time problem. What is that? It is a problem that can be solved and verified by an algorithm in polynomial time. Polynomial time means the running time of the algorithm is polynomial in a polynomial function of the input size. Let's take a look at the example of polynomial time. O n squared, O n log n, O n, and O n cubed is the example of polynomial time. And for non-polynomial time, the example is O2 to the power of n and O3 to the power of n. We also can call this usually an exponential time. And what is the difference? Here we can see the difference in graph between polynomial time versus non-polynomial time complexity. In the blue one, as we can see, is O2 to the power of n, which is the non-polynomial time, and O n square is the polynomial time. We can see the great difference between these two. And second of all, we also will discuss about the example of P problems. The problems are sorting problems, searching and searching problems. And the algorithm used for this problem is binary search for searching problems, and for sorting problems is merge sort, quick sort, and bubble sort. Each of these problems have a polynomial approach of it, which is O with the worst case of O(n) for the binary search. For merge sort is O n log n, quick sort O n square, and bubble sort is also O n square. And the verification of this is basically O to the n. How we check it is as we can see, this is a sorted number, and if we want to check a sorted number, we just can verify it by basically knowing that the left one is greater than the right one. Then it will be O with time complexity O n. And for NP problem, what is an NP problem, or what are the NP problems? NP problems are the non-deterministic polynomial time problems. These are problems that maybe cannot be solved in polynomial time but can be verified in polynomial time. The example of this problem is the traveling salesman problem, or TSP, as an NP problem. This problem includes a list of cities and the distance between them, and a number k. Is there a route that visits each city exactly once and travels a total distance of at most k? In finding this problem, we can verify it with the complexity O n log n, which is still in the polynomial time. And the solution? Currently, we still don't have the solution, so we just brute force it. For TSP problems, to verify this TSP... Sorry, okay, one more, for you. TSP problem. How actually we can verify a TSP problem? To calculate the total distance, because we have 4 vertices, so we just need O n. And to check if every vertex is visited only once, for each vertices, we need a complexity of O log n. Combining this, we will get a complexity of O log n, which is a polynomial time. But the solution for this, because we have only the brute force approach and still don't have an algorithm to find actually the shortest path. So the solution of this is O n factorial, with n the vertices of, or the series of this problem.
Now, let's focus on NP-hard problems for a moment. NP-hard, or also known as the non-deterministic polynomial time hardness, is defined as one where every problem in NP can be reduced to it in polynomial time. This means that the NP-hard problems are at least as hard as the hardest problems in NP. But there's a catch. The NP-hard problems aren't necessarily in NP. Why is that? It's because they're not required to have solutions verifiable in polynomial time. For instance, some NP-hard problems take so long to verify or solve that they don't even qualify as NP problem itself. Now, let's talk about the NP-complete problem. It's a special subset of the NP problem itself. A problem in NP is called NP-complete if every other problem in NP can be transformed or reduced to its polynomial time. These are the hardest problems in NP because solving an NP-complete problem efficiently would mean you are supposed to solve every NP problem efficiently as well. For instance, the traveling salesman problem and the knapsack problem are the NP-complete problems. They are the final step in solving all NP problems, making them critical to understand the computational complexity. Now, let's dive into the central question, P versus NP. But before that, let's have a quick recap. P, which is the problem solved in polynomial time, and P, which is the problems verified in polynomial time. NP complete is the hardest problem in NP, both in NP and as hard as NP problem. And last but not least, the NP hard is the problem as hard as NP problems, but not necessarily in NP itself. But the question is, does P equal to NP? So if P equals to NP, then every problem for which we can verify solutions efficiently could also be solved efficiently.
The P versus NP problem or argument whether P is equals to NP or P is not equals to NP is essentially asking that can every problem that can be verified quickly or in a polynomial time can also be solved quickly or in a polynomial time. Let's see if P equals to NP. Every problem in NP problem exists an algorithm that acquires the solution of NP problem to be done in polynomial time problems and can be solved in polynomial time, but we haven't found it yet. Or P is not equal to NP, meaning that only some of NP problem can be solved in polynomial time, while the others, we can't solve it in polynomial time. To more understand this, let's take an example of a Sudoku game as it is an NP problem. Imagine you are given a Sudoku puzzle, a 9 times 9 grid of numbers where some numbers are already filled in, and your task is to fill the rest of the following rows. Each row, each columns, and each 3 times 3 subgrid must contain the digits 1 through 9 exactly once. The verification of a completed Sudoku puzzle can be done in polynomial time, so it is an NP problem. In Sudoku, to verify, you need to just check, as I said just now, are the rows valid, are the columns valid, and are the subsets valid. What if P equals NP? Even though it's easy to verify whether a completed Sudoku puzzle is valid, finding the correct placement of numbers in the first place is hard. And P equals to NP means that finding the solution of this problem in polynomial time is possible, even when more rows are added or even exponentially bigger. So, P equals to NP means that finding the solution of this problem is polynomial time possible. While Sudoku provides a good example of an NP problem, it's important to note that the implication of P equals to NP extend far beyond puzzles. NP hard problems represent the peak of computational complexity, and solving them efficiently would revolutionize many fields.
Now, what if an NP hard problem has a polynomial time solution algorithm? Now, what happens if we discover a polynomial time algorithm for an NP hard problem? This would imply that P equals to NP. Why? It's because that NP-hard problems are as hard as any NP problem. Solving one NP-hard problem efficiently means we can solve every NP problem efficiently by reducing it to the NP-hard problem. But however, even we even we sorry even if we had such an algorithm, we to verify the solution for the hardest NP-hard problems could still require, well, we could say some sort of magic due to the complexity that is very complex.
But will it impact the verification of NP-hard problems? If we found a polynomial time solution algorithm, the answer is still no. It is most likely it will not impact the verification. Therefore, the verification of some NP-hard problems might still be hard. This is because the verification of solution doesn't always become simpler just because you already found the solution in a polynomial time of it.
But do you know what field this will impact the most? Well, surprisingly, cryptography is the field that it really impacts the most. So let's talk about how solving NP-hard problems in polynomial time will impact the field of cryptography, a cornerstone of modern digital security. Now, cryptography is the science of securing information through mathematical techniques. It underpins the security of online banking, encrypted messaging, digital signatures, and many more. But cryptography relies heavily on one crucial assignment. Certain mathematical problems are hard to solve in polynomial time. So, why is this reliance on hard problems so important? Now, the strength of many cryptographic systems depend on how computationally challenging it is to break them. In particular, modern cryptography often uses problems that are either NP-hard, where these problems are at least as difficult as the hardest problems in NP, believed to be intractable. Even if they're not proven to be NP-hard, they are practically unsolvable within a reasonable time frame for large inputs. Some of the critical problems used in cryptography included are factorization of large numbers, where breaking RSA encryption involves factoring a large number into its prime components, while multiplying two prime numbers is easy, but reversing the process factoring is computationally very challenging and hard. Next is discrete logarithms. Many cryptographic systems like Diffie-Hellman key exchange rely on difficulty of solving discrete logarithms. This involves finding the exponent in a modular arithmetic equations, which becomes exponentially harder as the number grows itself. And the third of all is finding optimal paths in graphs, where some cryptographic methods tie into NP-hard problems like finding specific optimal paths in complex graphs. These problems are inherently difficult to solve efficiently. Now, how does cryptography relies on hardness, which we are going to go into a closer look and deeper look into it. As I said before, cryptography is built on the premise that certain mathematical problems are extremely difficult to solve, especially as the input size grows. These problems are computationally intractable, meaning they will take an impractical amount of time to solve using current algorithms and some sort of computational power. Now, why hard problems are essential in cryptography? So in cryptographic systems like RSA encryption, it depends on the assumption that solving specific problems such as prime factorization is computationally hard. This hardness is what makes encrypted data secure, and without this, attackers could easily decrypt sensitive information. But what happens if hardness breaks? If an NP-hard problem like prime factorizations can suddenly be solved in polynomial time, the security of cryptographic system collapses. Here's why. Now, many cryptographic methods, including public key encryption, seems rely on the difficulty of solving these problems. If a polynomial time algorithm is discovered, attackers could solve these problems efficiently, so it will render the encryption methods ineffective. Now, let's dive deeper into the broader implication on cryptography. Now, let's dive deeper into the broader implications on cryptography. Public key cryptography, a cornerstone of modern digital security, is designed around problems that are extremely difficult to solve. Many of these problems are assumed to be NP-hard or computationally intractable in practice. So, why cryptography depends on this hardness? The security of public key cryptography schemes such as RSA and elliptic curve cryptography relies on the assumption that certain problems like prime factorizations or discrete logarithms cannot be solved efficiently. This computational difficulty is what ensures that encrypted data remains secure from the attackers. Now, what happens is the NP-hard problems become easy. So if a polynomial time algorithms are discovered for solving NP-hard problems, it will undermine the fundamental assumption of cryptographic security. So first of all, breaking public key encryptions, like systems like RSA, which rely on the hardest of factoring large numbers, would become very vulnerable. It compromised digital security, where it encrypts communications, online banking, and secure data storage could all be at risk, as attackers could efficiently decrypt data. Now, rebuilding cryptography to counter this risk, cryptographers will need to develop new cryptographic methods that rely on problems remaining hard, even in a world where polynomial time algorithms for NP-hard problems exist. Well, we could say that this could involve such as exploring problems in classes beyond NP-hard, such as quantum-resistant algorithms, and where it designs cryptographic schemes based on physical principles or new computational paradigms. Now, finding polynomial time solutions for NP-hard problems would be a groundbreaking achievement in computer science, where it opened doors to advancements in optimizations, artificial intelligence, or AI, and other fields itself. But, however, it will also bring significant challenges, particularly in cryptography, where the security data depends on the difficulty of solving this problem itself. Even if solutions could be computed efficiently, the verification process might remain very complex, and implementing these solutions in practical systems would pose its own difficulties. Now, for what us to really remember is that, most importantly, the real-world impact would be profound in areas like digital security, as many cryptographic systems are built on the assumption that some problems are computationally infeasible. If these assumptions were to collapse, the security of sensitive information, financial systems, the global communications networks will be at a very high risk. It will highlight the delicate balance between the theoretical breakthroughs and the practical consequences. Now, to end our presentation, we would like to state some takeaways. If P equals to NP and polynomial time algorithms were found for NP-hard problems, it will fundamentally transform how we approach computational challenges. In the context of digital security, the change will be monumental. Now, cryptographic systems relying on the difficulty of NP-hard problems will no longer be secure. Data privacy and online security will face unprecedented risk, impacting individuals, business, and government itself. Now, beyond cryptography, the effects will ripple across the digital economy, where it will suddenly disrupt the systems that rely on secure transactions, encrypt communications, and trusted digital signatures. While this breakthrough could revolutionize algorithms and optimizations, solving problems previously through um, solving problems previously thought impossible, it was simultaneously depend everything of how we secure information in an interconnected world. Now, the balance between progress and the security will become a critical challenge for the future ahead. And with that, we like to end our presentation and we like to say thank you very much for your attention.